This is work funded by the Plant Biosecurity CRC, and it's I suppose the culmination of quite a few years' work on looking at biosecurity. So what we were asked to do in this project is to look at some past pest incursions and try and start to understand whether the decisions that were made at the time of the incursions were the right ones. And I suppose you start off on these research projects feeling fairly optimistic, but then you soon realise that these questions are very, very complicated, and so I suppose inevitably you end up going into survival mode and say, well, what possibly can we say about this problem? Now, why was this so difficult? Well, it emerged that when you're looking at biosecurity management, then really the key thing is information, and it's information through time and information across a spatial area. And when I looked at the economics of surveillance and the economics of information, there wasn't a right lot there, to be honest, in terms of a microeconomics of how you value knowing something sooner rather than later. And then when I started looking at started to do the microeconomics, it turned out to be really complicated. And so after a series of sort of failures, then what I ended up with is about the simplest model possible, and I got rid of the equations for this seminar, and I'm just going to do it just going to look at the model in graphs. And then I built a bigger simulation model, which was actually able to sort of represent the microeconomics, but not necessarily explain it very well. So that's where we are. That's where we are now. Okay, so what am I going to cover? A short history of incursion management, using some quick case studies. My version of the theoretical model, which could be subtitled "The Economics of Information on What is Known by Whom and When, and Did They Fight the Battle or Just Form a Committee?" And committees were quite often formed while the pests thrived and blossomed and basically took over. And then we'll focus in on the main case study, which is Khpara beetle in Western Australia, and this is an application of simulated annealing, where we're trying to get out some approximately optimal solutions. As it turns out, but very approximate. Okay. So past. So what do I have in mind when we're looking at these pest incursions? And so we tend to think about a series of. And when I say we, I should have mentioned my co-author on this paper, and the person who's responsible for the good slides. The crappy slides are entirely my responsibility. So Cheryl, so we tend to think of sort of past battles. So there was a WA potato cyst nematode incursion, successfully eradicated, cost about $1 million. But then was followed up by 20 years of surveillance, so that was additional costs. There was a Victorian potato cyst nematode incursion, 1991, failed eradication, cost about $2 million, plus about $3 million in soil sampling, still causing massive production losses to the industry. So Emerald, Queensland, citrus canker. That was a successful eradication after $47 million of costs, and basically closing the closing the citrus industry in that area. Yarra Valley, Victoria, grape phylloxera, this weird little aphid that goes and sits on the roots of grapevines. Failed eradication, attempted containment. We don't know what the costs are, but you could say safely probably in the tens of millions by the time it's run its course. Warehouse beetle, Western Australia, New South Wales, found in canola, stored food, supermarkets. Failed eradication, cost about 2 million. Similar to Khpra beetle, but it actually flies, and the ability to fly turns out to be important. And then this is my favourite example, California and US and Mexico, Khpra beetle, 1953 to 1966. So the Khpra beetle, the destroyer, it's and we'll come onto this later, but really the grain pest from hell. Not susceptible to any standard treatments, basically goes into a dormant, non-vulnerable state, so you can't zap it with anything. You know, once you've got it in the system, really difficult, expensive to get out. Cost about somewhere between 96 million to 130 million US dollars, 2016 dollars. And then there's our incursion, which is the Perth Khpra beetle.
Did the Americans eradicate it?
Yes, they did. This is my favourite biosecurity picture. What did the Americans spend, you know, over $100 million on? This pest was so bad that they applied methyl bromide, which is a fairly nasty chemical, internally on their grain silos, and they dug earth for about 30 to 100 metres around the grain stores and applied something equally unpleasant to that. But they also, and this was repeated across California, they also they manufactured tarpaulins that could fit over grain stores so that they could get the concentrations of methyl bromide up high enough to go and kill these blasted beetles in the sort of nooks and crannies in the grain store, because Khpra beetle has this ability to, well, go to sleep, and also this ability to hide and avoid fumigation. So this is what they did. I mean, it was a massive, but they eradicated. And every time in the US Khpra beetle has appeared, they've eradicated it.
And no natural predator?
None that's able to keep up with the rate of population growth that you find in. I mean, grain stores are basically unlimited food for grain beetles, so their populations can really take off. Okay, so that's the fun stuff. So we have to just run through a simple theoretical model, and then that's a lead into the Khpra beetle case study. Okay, so how do we protect ourselves against pests like Khpra beetle, and how do we manage them? Well, I suppose there's a cycle of things that are going on. So protecting Australia is border surveillance, which is what you encounter when you're at Perth Airport and you look down to your feet and you see a beagle sat on your shoes, looking up at you, and then followed by a quarantine officer who then wants to inspect your bags. So that's the sort of border surveillance that goes on. So checking of bags, asking of questions, but it's very generic. So they're not putting out pheromone traps for Khpra beetle. They're just trying to pick up anything in general. So there is a possibility that stuff gets through, and with the volume of passengers, the volume of container trade that's coming into Perth, then incursions are almost inevitable. Okay, especially for things that are not actually that large. I mean, a Khpra beetle is pretty small.
Sorry, where are they coming from expected?
They're fairly ubiquitous, but probably India, Pakistan. The Perth incursion actually came from Pakistan, it is thought. Okay, so once something gets through and becomes a post-border incursion, so it pops up possibly in a house in Perth, then why is it detected? Well, I identify something called natural surveillance, and this is literally that a householder or a farmer or some member of the general public spots something unusual, and this process can often take quite a long time. So this Khpra beetle was found in the house of some recent immigrants from Scotland, and they said, and I'm not going to attempt a Scottish accent, you'll be pleased to hear, but hey Jimmy, there's fair few beetles around, man. I hen. Yeah, so someone spotted literally there were lots of beetles around, got a pest guy in. Pest guy had been on a course with WA and spotted that it was not the usual warehouse beetle or the usual sort of pest that you'd find in a bag of flour. So that's an example of natural surveillance. It's something being picked up by the general. So that then leads to a positive detection, and then that triggers something I'm calling precautionary surveillance, which is you then up the surveillance in the property where the pest is found, and then you up the surveillance in the surrounding properties. Now that then starts to cost you money because you've got WA officers who are out checking traps, and the traps themselves are quite expensive. So you have to get specialist pheromone traps for Khpra beetles, which fortunately are available. And then once the pest has been identified, then it goes through a process of eradication, which can be pretty complicated. So it's in the property where the pest is. Sometimes they'll carry on applying eradication in surrounding areas, possibly to surrounding properties, although that didn't happen. And they have to also do what's called trace forward and trace back, which I think with Khpra beetle led them into Queensland to work out where the containers had gone to, and I think they went to Norway as well. Was that right? Yeah, about 5 destinations, just checking that this beetle wasn't still there. So very, very expensive. Okay, so here's our version of a simple model, and this just includes the damage cost. A fuller model also includes the eradication cost. So we're looking through time, which can be quite a short time period, and we've got population up the vertical axis, and because it's a linear function of the population, we've also got damage cost up the other vertical axis. So just giving the numbers as numbers of beetles and dollars. So as the population grows, there's a possibility of the pest jumping between properties. So the incursion on one property can lead to an incursion on another property with associated damage that's increasing through time as the pest population increases. How is something picked up? Well, natural detection, you know, there's edge, I mean, there's lots of beetles around, sort of thing. So that's natural detection. So that then means that once that's been passed on to someone who can do something, then that triggers eradication. And then you start to apply precautionary surveillance. And the difference between natural surveillance and precautionary surveillance is that I'd say precautionary surveillance is much more sensitive to low populations of beetles. So because it's using a pheromone trap, it might pick up really quite low population densities for beetles. And so if you've got precautionary surveillance in place, then the pest is detected at a lower population density. The pest is detected at an earlier time than would otherwise be the case, because otherwise you're just depending on natural detection. So you get more damage, and you get the pest being detected at a higher population. And what happens there is that we get, if we take this area here, then that's giving us a saving of pest in terms of pest damage. Okay, so this is my simple version of the economics of surveillance. Increases sensitivity to low pest populations, means that a pest is detected sooner rather than later, and it gives options. So the regulator, DWA, or other state departments of agriculture, can then decide to engage in eradication, additional surveillance, or they could set up a committee and talk about it, which might sound strange, but that's what actually happened with PCN in Victoria, and is still happening. Okay, so how do we characterise Khpra beetle? So I don't know if any of you know this character, Jim Royal from the Royal family, who's a Liverpudlian who spends most of his time on a couch, drinking and generally being miserable. So I think that's a fairly good personification of Khpra beetle. So Khpra beetle, it's overfed, lazy, hairy. It's a bit of a slob of a pest, and it doesn't actually like moving very far. But what it does like doing is breeding. So it has quite a rapid population growth. But the reason it's such a massive pest is, well, it's breeding because it produces lots of larvae, and it also likes to molt, so it tends to leave lots of dead skin around the place. And it tends to do lots of damage if it gets into a grain store. So you get areas of a grain store which are just not fit for human consumption, and then you get whole sets of storage problems such as moisture increases and so on. Okay, so this is what the actual pest looks like. You see remarkable resemblance, apart from it hasn't got the hands to hold beer yet, but it's probably evolving those as we speak. It's also pretty small, yeah. I don't think Jim was ever particularly small. So, least wanted pest of stored grain, infests a very wide range of stored food, but it's pretty tiny for something so small. It does cause a lot of damage, and it doesn't fly. It just walks around. These are the larvae. Runs through 5 molts, which leaves skin everywhere in grain. Produces various amounts of excrement, and can go into diapause for up to 6 years, and that's quite important as well because it makes it difficult to eradicate, and it has serious trade implications. So no one wants this pest. because they know that they're going to be up for a massive bill in terms of trying to eradicate it. Okay, so what happened in Perth? Well, it was an incredibly small incursion, but it cost $200,000. And in fact, the incursion was found in the rented property of this family that had just come from Scotland. The response by WA was to wrap the house in cling film, and this was to maintain the concentrations of methyl bromide, and then they fumigated a very high concentration of methyl bromide. They managed to destroy all the furnishings and carpets in the house because there was a chemical reaction, and so this was a fairly massive expense for what was a very limited eradication. So this represents the mean streets of Scarborough. Vero's not here, is she? No, so this represents the mean streets of Scarborough, and what we've done to analyse this problem is that we've taken a cookie cutter circle around the house, which is based on how far we can expect this rather lazy pest to actually move. So it could sort of feasibly move slowly between houses. So it can walk between houses, but of course one of the main forms of movement is if anyone ever sort of borrows a bag of flour from someone else, so you can get human movement between properties. So that's the means of spread. In fact, Khpara beetle has almost co-evolved with humans to use people as its means of dispersal between potential habitats. 500 metres, yeah. So yeah, they cross across here. I think we possibly do we have a CSRO Christmas party in one of these houses? I can't. Anyway, you turned up late, Sarada, so you probably. No, I don't think I bathed. Okay. Now, in a bunch of houses, then Khpara beetles is just a minor annoyance, but of course, there's always this possibility of human-mediated movement to the wider grain system, and that's where the really big costs start to kick in. So there's always the possibility that someone from Scarborough will, by some means, move the pest from the metro origins into one of these, these grain farms, which are the small dots here, and more worryingly to one of these grain receival sites. So the black dots are grain receival sites, and I think the round dots are the major ones, and so they're just grain receival sites. Okay. So this is a timeline for what happens. So before these pests come in, there's an emergency plan, so that State Department officers know pretty well what to do, and then they engage in an information gathering stage once an incursion has arrived. And this was actually quite a short period. It was like 2 days. They then confirmed and developed a response plan. And so 18th of April, the pest is discovered. By early May, then they were into this quite expensive process of eradication, surveillance, fumigation, tracing forward, tracing back. And then following that, they engaged in a 2-year trapping program just to double check that the pest had been eradicated. And so currently, as far as we know, we're Khpra beetle free. You can breathe easy. So okay, so we developed a model of Scarborough. And these are the list of equations that I'm saving you from. So, these are the components. So, we've got pest population growth. So that's basically growth, population growth within a property. There's a jump diffusion. So the pest can, with some probability, jump between households. And then there's eradication, which is fumigation, and that's again a random activity in that you could get some escapees. Detection depends on the surveillance level. So if you're just operating at natural surveillance, then you could well be up to a couple of hundred beetles or even 1,000 beetles before things are actually triggered. And so that's also random. And then there's an external cost, which is another one of these jump processes where instead of jumping between properties, then we're looking at the slight probability of this larger jump from Scarborough into the grain supply network, which is the thing we're really worried about. Okay, so we went through the accounts for the original incursion, and these were the best guesses we had for the possible for the policy variables and their cost. So eradication, you could do nothing. You could let the pest spread, and then hang on, I've just I lost a slide somewhere. I need to go forward a bit. Okay. So I've just got my slides out of order because I didn't do a practice as recommended by Cheryl. Okay. So we use this method called simulated annealing, which was I first heard about when Graham Dooll applied it in his PhD. So to me, what it allows you to do is you have a simulation model, and in our case, the simulation model is simulating the link between an incursion, which we fix. We then have population growth within properties, and we have jump between properties. So it's a spatial and dynamic model, so quite complicated, and it also has this possibility of jumps externally, which then incur costs as farms and grain stores are fixed up. So that's the simulation model. And then we use simulated annealing to basically just run through sets of policies to see which one gives us the best solution. So it's essentially a random search, and if a policy gives a lower cost, then it's accepted. But occasionally, if a policy gives a slightly higher cost, then it might also be accepted. And the reason that simulated annealing does that is it prevents the solution getting stuck in local optima, locally optimal solutions, which are not globally optimal. So what it does is it allows you to allows you to have quite a wide search initially, and to find the best value. And then as the iterations goes on, it sort of narrows. It tends to constrain things more and more, so that you hopefully converge on an optimal solution. And it has this physical analogy, which is about cooling metal down, and the atoms that there are within metal settling into crystalline forms. Okay, so now going back. So we ran simulated annealing, and we found that the optimal solution was to go for a moderate level of eradication, that is spray, but not wrap and spray. So there was just three options here: do nothing, moderate eradication, and then the highest level of eradication, which was both wrapping and spraying. And then surveillance intensity index was about the number of times that you go back to the houses to check the traps, and it actually had a very moderate level of surveillance, suggesting that with this pest, natural surveillance pretty well might be enough. The actual full surveillance that was used by WA was about $611 per visit by the time you'd taken into account the cost of travel, the cost of the traps, etc. The external costs so we have this distance between grain stores, and we use distance as a measure of the probability that you're going to get a pest moving from the metro area out to a farm or a grain store. We had a pretty simple estimate of this. So for grain stores, it was $1 per tonne plus a fixed cost of setting it up. And if you just remember back to the California example, it's all those costs of sealing these fairly low-tech grain stores that there are out in the wheat belt. And then if you look at eradicating it from a farm, well, actually, it's effectively the same as eradicating it from a house. You're just Khpra beetle, lazy slob of a pest. It's not going to be wandering out to fields. It's not going to be flying around. It's going to be around farm buildings where it's got a ready supply, where it's nice and warm, and it's got a ready supply of grain. Okay. Okay. So modelling strategy. So we're looking over 2 years of weekly time steps, because that was the time step that was relevant to the eradication problem. We used simulated annealing to find the best policy decision variables over a large number of simulated incursions, and then we re-simulate the best solution to check the distribution of cost outcomes. So I just so we've got here we've got five possible. We've actually got 5 possible decision variables. We've got the eradication options. We can do precautionary eradication. So that's going, and you can imagine how popular this would be. So go and wrap the neighbours' houses in cling film and engage in a methyl bromide fumigation without the pest being there. Might make sense, but it wouldn't be popular. So precautionary eradication, we've got the surveillance intensity, we've got the precautionary surveillance cutoff. So what this does is it says, well, if you've got a pest in a house, how many houses around it do you subject to this additional surveillance? with additional costs because you have to go and visit them, you have to have the traps there. So how many additional houses do you involve in that? And then we also had this precautionary surveillance stand-down rate. So what WA did is they started off with very intensive surveillance. They were going visiting every week, and then as the number of negative observations, started to build up, they were going back, finding nothing, going back, finding nothing, then they gradually started to make that less frequent. I think they went to monthly. They went to monthly surveillance. So that's why we have this stand-down rate. And the lower bound gives the lower bound of the policy parameter that we looked at, and then this is the upper bound on the policy parameter. So, for instance, surveillance intensity is an index between 0 and 1. It's an index between natural surveillance, which is fixed at 0.5 and 1. Correct myself there. Surveillance intensity between natural surveillance and 1, because you do get some surveillance for free because people notice stuff. And then the precautionary surveillance cutoff is the lower bound is you just do the infested house. The upper bound is that you do the whole cookie cutter area. Precautionary surveillance stand down is between 0 and 1. Precautionary surveillance cutoff is again the infested house through to the whole suburb. So I think.
What's the unit for that? How do I interpret what that means?
Sorry.
Precautionary. Was the last one?
This one. Yeah. So you engage in surveillance.
I heard the story where you get less and less surveillance.
Yeah.
But what does 0.72 mean?
Yeah. So it just means that the frequency of visiting goes down by 30% in each time period.
Okay.
Yeah. So these are these are the optimal solution, the least cost solution, and we also had a look at what I called a low cost set, which is where you increased eradication to the Rolls-Royce wrapping cling film eradication, and you made the surveillance intensity 1, but you still and also this was a bit odd, but we reduced this precautionary surveillance to just being approximately 3 houses around, because we thought I thought the 200 metres was unrealistic. But I'll perhaps come back to that in questions. This is what some simulations look like. So these purple dots are mean streets of Scarborough. So those are the houses that haven't got anything. And then it's not very interesting really. They just got a couple of light blue dots that indicate some pest population is there. And then this evolves through time. So this house has still got some, and then the pest pops up here, sort of 2 weeks later, and then by week 4, then the pest is popping up in 4 places. And then if I run the simulation on, then by 10 weeks, in this simulation, the eradication has gone. If we do the Monte Carlo simulation on the optimal policy and on what I've called the low risk policy, then the optimal policy you'll notice is low cost. So most of the scenarios, or most of the runs, are giving costs of around about $50,000, with some up at 150,000, and then you've got with this one you've got a few really bad ones where you've had the pest jump to a grain store or to a farm. So that's where you get this set of incursions that are around about sort of 19 million. With the low risk policy, then it's on average it's more expensive, so it's more like 300,000 than 50,000, but you're chopping off these high risk events. So we've got some more analysis to do on that, and I need to finish. And these are just what's happening to the other costs, the distribution of other costs for the Monte Carlo simulation. So we can break the cost down into surveillance, eradication, and external costs, and we could do this for the optimal policy and what we're calling the low risk policy. Okay. So this is quite a difficult problem. It's nasty, stochastic, spatial, and temporal in nature. Quite hard to determine an optimal policy set. That's why we used simulated annealing. Information, however it's derived, either by natural surveillance or precautionary surveillance, is key. Without information, then actions can't be taken and are likely to be wasteful. Generic surveillance at port is probably just too expensive, because there are about 10 million pests in the world that are fancying Australia as a home, and so you'd have to have huge batteries of traps to try and pick them up. And underneath all this, then I think in policy terms, then you have a trade-off between cost and risk, which is what we're starting to explore. Okay, thank you very much.